So welcome to Demography Today lecture series, sponsored by the VVA Foundation and organized in coordination with the Lompop Horizon 2020 project. And we have the real pleasure to have today here Aubrey de Grey, who made a space in his very busy agenda to be here with us for some hours. Aubrey de Grey doesn't need much introduction because he's quite famous internationally. He is a biomedical gerontologist based in Mountain View, California, USA, and is the chief science officer of Sense Research Foundation, which is a California-based biomedical research charity that performs and funds laboratory research dedicated to combating the aging process. He is editor-in-chief for Rejuvenation Research, the world's highest impact peer-reviewed journal focused on intervention in aging. He has his BA in computer science and his PhD in biology from the University of Cambridge. His research interests encompass the characterization of all the types of cell-inflicted cellular and molecular damage that constitute mammalian aging and the design of interventions to repair and or obviate that damage. Dr. de Grey is a fellow of both the Gerontological Society of America and the American Aging Association, and sits on the editorial and scientific advisory boards of numerous journals and organizations. As I mentioned, he's quite famous. He was just mentioning that he's just moving from here to Barcelona tomorrow, and then to different countries in Europe just to give lectures. And he was here during the weekend on another conference, and as well presenting this book that you can download as well from the BVA Foundation Open Mind webpage. So thank you very much, Aubrey. And as usual, we allow the speakers just to have plenty of freedom, 1 hour, 15 minutes, and then we will open the floor for questions.
I understand that this audience is quite varied in terms of expertise in demography, so I am going to copy that with my talk. I will have quite a bit of material which is rather technical, and it may be difficult for some of you to understand all of it, but I will also have plenty of things to say which are very much more general and non-technical. I hope that's okay. The final thing I want to apologize for is that this is the first time that I have given this particular talk. Many of you may know that I am really a biologist. I am not a demographer. But I do demography for fun sometimes. And I am going to present today some new ideas which I think are valuable, but I could be wrong. But the point is, I have never presented them before. So, of course, that is a good thing and a bad thing. It's a good thing in that you have the luxury, the privilege of being the first people to hear these ideas. But it's a bad thing because I'm going to present them very badly, because I've never done it before. So we will see how it goes. All right, so is this a laser pointer in any sense? Not really. Okay. Right, so this is what I'm going to do. I'm going to talk about the limits to human longevity. The very longest lived people, what we can learn about them, and in particular, what we can learn about their ages at death, the age at which they died. The topic is very fashionable. Many people think about it and talk about it a lot, and I'm going to try to tell you something useful about it. And of course, the main reason why people are so interested in it is because they have a feeling, a kind of intuition, that if we study the ages that people can currently get to, we might get some ideas about how to do better than that, how to develop medicines and such like that would help us all to live longer, healthier lives, which everybody wants. So I'm going to start with a few little pieces of data. The first thing I'm going to mention is the current world record for longevity. which is held by a lady from the south of France named Jeanne Calment. She died at age 122 years and 164 days. So nearly 122 and a half. And that record has not even been nearly approached, let alone beaten, since then. She died 20 years ago in 1997. Today, the world record for how old somebody is who is alive today is held by a Jamaican lady named Violet Brown, and she is more than 5 years younger. And actually, only, I think, 3 people have got closer than that to Jeanne Calment in 20 years. So it's a pretty amazing data point. And it's particularly amazing if we think about people who are slightly younger. We all know that people are living longer than they used to. But if we drill down a little bit and we try to ask, in what way are they living longer? Who is living longer? Then we come up with some very interesting conclusions. There are a higher proportion of the population gets to 60 than 50 years ago. And a higher proportion of the population gets to 70 than they did 50 years ago. But the difference is bigger at 70 than it is at 60. In other words, the whole population is getting more biased towards older ages. And that phenomenon extends. The proportion of people who get to 80 is much bigger than it was 50 years ago. And the proportion of people who get to 90, of course it's much smaller than the proportion who get to 80, but it's enormously bigger than the proportion who got to 90 50 years ago. And so on. It's true for 100. There are perhaps, if we even look at a difference of 20 years, in other words, now versus 20 years ago, there are at least 3 times more people in the world today who are over 100 than there were 20 years ago. So, what's going on? Why aren't we constantly beating the world record for longevity? It's very strange. And it's something that we ought to be studying. We ought to be trying to understand what's really going on, whether there is some kind of biological limit to to how long people can live. If there is, then people like me, biologists, should be studying it and should be figuring out the basis of it so that we can fix it. But we need to know whether it's really there, first of all. And that's a big problem. Because in order to study anything in science, you need reliable data. And there is almost nothing in the whole of science in which it is harder to get reliable data than extreme longevity. Because everybody lies about their age. I mean, like everybody. It's just insane. Some people want to pretend that they're younger than they are. Some people want to pretend that they're older than they are. And in particular, an awful lot of people who are very old want to pretend that they're even older. And people are good at pretending this thing. So you can end up in a situation where people it's really clear that somebody really is the age that they say they are. And then 10 years or 20 years later, it turns out that actually that was the age of their brother, or something like that. That's exactly what happened with this guy called Izumi in Japan. So if you look at the Guinness Book of Records from, let's say, the year 2000, you will find that the second oldest person ever is this guy from Japan called Izumi, who lived to 120, only 2 years less than Calment. But it's nonsense. It's just not true. It turned out, about 10 years ago, that it was actually his brother. And that was, it was well enough verified that it got into the Guinness Book of Records. So it wasn't just somebody said so. And this happens all the time. So we need a system, we need to develop a system for verifying data about people's ages. Now, of course, as time goes on, it becomes progressively easier. More and more countries have data on the date of birth and the date of marriage and other things, census reports and so on, that's really, really solid. So it becomes easier to make sure that the dates that people say they lived to, they really did. But still, in most countries in the world, that's not quite true. You know, at the moment, the oldest person in the world was born in 1900. And in 1900, not very many countries cared very much about this kind of thing. So the records are really patchy. And of course, in many, many big countries, the records are almost non-existent way back then. So it's very hard. However, more than that, we need balance. At the end of the day, the reason we care about this is in order to be able to identify trends, to identify what is happening in this data. And you don't need totally comprehensive data to do that. You just need to try to make sure that the false negatives and the false positives cancel each other out reasonably well. In other words, that the people you are believing when you shouldn't are about as numerous as the people you're not believing when you should. If you can do that, then you're kind of okay. And in particular, what this means is you want to... I'm going to sneeze, I'm sorry. Okay. You want to avoid systematic bias. It could be, for example, that the things that you're believing are mainly male longevity, and the things that you're disbelieving are mainly female longevity. And that would be a big problem. You know, you'd really mess up. And that kind of thing could happen. For example, some of you may know that there are certain places in the world where life expectancy at birth is a bit higher than in the surrounding population. Okinawa is a famous example of this, an island at the southern end of Japan where they live nearly 2 years longer than the rest of Japan. There are various places like this. And one of those places, a part of Sardinia, is particularly famous because of the gender ratio. You almost certainly know that almost everybody who lives to 110 is female, like 90% or more are female. At least 80% of the people who live to 100 are female. Just women tend to live a bit longer. But in this one place in Sardinia, it's not like that. The men live just as long as the women, even out to the age of 100 or 105. And nobody has the faintest idea why. So, you know, it's a really important thing to study, but it could easily have been missed if you were oversimplistic about gathering data. So we have to be really careful about this. Now, who does this? How do we get to be really careful about it? Well, the good news is that extreme longevity is fascinating not only to academics, but to the general public. And some members of the general public have time and money or whatever to actually dedicate themselves to this. And the result is that over the past 20 years or so, a group has emerged which is centered in Los Angeles, California. It's called the Los Angeles Gerontology Research Group. And almost all of them are not academics. They are just people from the general public with other jobs. But they're really interested in all of this. And over the years, they have become really good at sifting out the data, at getting to the bottom of whether a particular report of somebody's longevity is true. And they have become really well respected. Pretty much everybody in the world now agrees that these people know what they're talking about. So they have become the world authority for the validity of a claim to live to 110 or greater. That's the definition of the word supercentenarian. Furthermore, they provide multiple levels of validation. So there are people who are absolutely hard, ironclad valid, they are totally certain that this is true. And then there are people where the level of documentation is not quite so good, but it kind of looks okay, and they think that it's worth mentioning these people in a kind of second-level data set. So, it's all pretty good. It could be better, but it's pretty good. The data are okay. So now, there's a problem. As I mentioned, lots of people are fascinated by the concept, by the whole area, by the whole topic of extreme longevity. Some of those people are professional demographers who know what they're doing. Some of them are amateurs who have spent plenty of time, who haven't got any qualifications, but they've spent plenty of time studying it, and they know what they're doing. But unfortunately, some of them are academics who think they know what they're doing, but they actually don't have a clue. And this is a good example. This is a paper that came out a few months ago. And, well, there's very little I can say that's printable about this paper. It was appallingly bad. This is a graph from this paper, and it got published in Nature, for crying out loud. I mean, in a very, very prominent journal. This is the author's attempt to derive some kind of fit to the data points that you can see on the screen, which are the average age at death of supercentenarians between 1967 or so and 2009 or so. And they fitted it, for whatever reason, using whatever a cubic smoothing spline is. I have no idea what that is. But anyway, my thought was, I had recently seen a cartoon on a comic strip called XKCD. I think this is probably about as good as... so for those of you who read English, the thing on the left is a regression, and the thing on the right is the same data points and a constellation in the sky. And it says, I don't trust linear regressions when it is harder to guess the direction of the correlation than it is to find new constellations on it. And that's about what I thought of that paper. So it's spectacularly embarrassing. It's so bad, it's just not true. But that's not what I came here to tell you. What I came here to tell you about is whether we can do better. And it's not obvious that we can do better, because the very definition of extreme longevity is that it's extreme. There are not many people who get to extreme lifespans. And, if you haven't got very much data, you can't do very much statistics. The nature of statistics is you need more data to get more reliable answers. So one might say, well, maybe it's a shame that people pretend to be able to derive actual conclusions from studying this small amount of data, when in fact they can't. But the fact is, they can't. Nobody can, because there's not enough data. So what I've come here to tell you today, and this is where I'm going to start getting pretty technical, is that actually we can do a lot more in terms of the analysis of this small amount of data than people have previously realized. Now, here is the fundamental problem. When you study the ages at death of people in a given population at a given range of ages, what you are really doing is you're trying to extract from that data a kind of generalization about the risk of death at any given age. You're trying to say, okay, here is the actual, you've got this certain number of people, a finite number of people, they died at these particular ages, but they might not have done. Anyone could have died at any particular age. What you want to extract from that is a probability of death that was experienced by each of those people at each age, which is called the mortality rate. And it turns out to be rather hard to do that with small amounts of data. If you have large amounts of data, it's not so bad. What you do is you just split up your data set by age. Typically, you might say, okay, here are the people that died at 110. Here are the people that died at 111. Here are the people that died at 112, and so on. And you simply ask, okay, out of all the people that were alive on their 110th birthday, what proportion of them didn't make it to their 111th birthday? And so on. That's the mortality rate. And if you do that, you can extract a set of data points for probabilities of death at each age. And you can ask questions about what that trend looks like. Does it go up? Are people more likely to die in their 111th year than they were in their 110th year, and so on? And, you know, these are important questions because you can actually make biological inferences from them. But if you have small amounts of data, you have a problem. Because with small amounts of data, you have what I'm calling here a tension between granularity and scatter. Now, what do I mean by that exactly? If you have this data set, then it's up to you what the size of your intervals of age are. The example I just gave was the standard one. People just say the interval will be 1 year. So you'll say these people died between their 110th birthday and their 111th birthday. But you didn't need to choose a year. You could have chosen a month. You could have said, okay, these people died in the first month after their 110th birthday. These people died in the second month, and so on. You're perfectly free to do that. But here's the thing. If you do that, of course, then you have fewer people in each of the slots, in each of the time intervals. And that means that you have more scatter. You have more, randomness in the data. So you have less ability to extract accurate probabilities from it. However, if you go the other way, if you choose large intervals so that you have large amounts of data points in each interval, you have a different problem. The problem you have is that you may simply smooth away the thing you're looking for. Supposing you want to find, for example, that the change with age is exponential or linear or logarithmic. If you're looking at the intervals are too small, you may not be able to tell because you're just not seeing. You're just throwing away the variation that you're looking for. So we need to try to avoid doing this. We need to try to minimize this tension between granularity and scatter if we are to get good information out of small data sets. So now I'm going to get a bit mathematical. I'm sure that every demographer in this room has heard of the Gompertz-Makeham equation, which was developed in 2 stages. First of all, by Benjamin Gompertz in the early 1800s, almost 200 years ago, and then refined a decade or 2 later by Makeham. And, of course, this is it, the equation for the mortality rate that is observed, the relationship between mortality rate and age that is observed in human populations, and indeed in the populations of laboratory animals. And it's a very simple thing. It says that the probability of death at age x, in other words, the mortality rate at age x, is the sum of 2 terms. One constant term, which is simply a number, and one exponential term, which is an exponential function of x, of the age. That's all that the Gompertz-Makeham equation says. And it turns out that it describes the risk of death in human populations really rather well over most of the lifespan of the population. You have to be a bit careful with it when you get to extreme ages because, of course, the mortality rate is a probability, which means that it cannot go larger than 1. And so you have a kind of mathematically enforced plateau that occurs. And the only way to get away from that is to chop your data set into smaller intervals, so that the probability of death in any interval is much smaller, and therefore you don't hit that plateau until later. But I'll talk about that later on. The main thing is that this equation really works. If you take any human data set, you always find that you can find values A, B, and C for which that equation really accurately predicts the number, or fits the number of people who died in the population at any given age. That's great. And everyone uses this equation all the time. But this equation here underneath it is an equation that I bet none of you have seen before. Hands up anyone who's seen that equation before. Right. Now, it turns out that that equation is the same as that equation. I got that equation just by integrating that equation. That's all I did. Px is the survival function. In other words, the proportion of the initial population that is alive at age X. Now, of course, that is simply the integral of the mortality rate, because the probability of dying each year is a probability. The probability of, the proportion of people who are alive at age X is simply the product of all the probabilities from 0 to X. 1 minus the probabilities. In other words, in order to get to age X, you have to have not died at age 0, and not died at age 1, and not died at age 2, and so on. So that's all that the survival function actually is. And this is simply the integral of that. That's all it is. Fine so far. But what the hell use is this horrible equation? Well, that's what I'm about to tell you. Here's that horrible equation again, right at the top. Now, I'm going to consider a particular type of data, of data on ages at death. It's going to be a situation in which these two things are true. Now, look at what those two things say. This one here says that the constant term, what's called the Makeham term, in the Gompertz-Makeham equation, is really small. It's saying that C is so small that for all of our data set, essentially this number here is much less than this number. That's the first thing I'm saying. Now, look at these two terms and find them in the original equation at the top. You can see that the original equation at the top has this big sub-formula here, which is the sum of these two terms. Now, that means that if this is much smaller than this, then we can just delete it from our equation, and we haven't changed things very much. We could just lose it, and we've still got something that's more or less the same equation, and is more or less an accurate description. Similarly, if we now look at this second criterion that I'm putting, where e to the power bx is much greater than 1, we have the same situation. Look at this formula here. If e to the bx is much bigger than 1, then let's just forget about the 1 and just call it e to the bx. So now here I have the version, the simplified version of this equation when I've done those two things. I have made these two assumptions, okay? And this is what I get as a result. A much simpler equation. That's great. But the big news is this. Because this is what you get if you take logs of this equation twice. You see there's an exponential term here and another one here. If you take logs of this equation twice, this is what you get. And look at it. It's linear in x. There's only one x in this equation. That is fabulous news, and I'm going to explain why it's fabulous news right now. Here is kind of a graphical illustration of what I've just told you, and why what I've just told you is useful. I'm going to go back and remind you of my criteria here. These are the assumptions I'm making. Now, are these assumptions true? In what circumstances are these assumptions true? Well, it turns out that in the scenario where we're studying older people, they are totally true. And that's what this graph shows you. As you can see, there are two plots here. There's a blue one and an orange one. And they're not plots of data. This is just purely the behavior of a hypothetical, perfectly Gompertz-Makeham population that has coefficients that are typical of human data. So see these numbers here, the slope of 0.1, that's pretty much exactly what human populations actually have. Intercept of 2 to the minus 4, 2 to the minus 4, and a Makeham term of 1 in 1,000. This is roughly what how human populations actually behave. And if you plot this as a survival curve, it looks like a normal survival curve. But what I've done here is I've plotted it in both of these ways. In the first way, I've plotted it as log mortality, which is what you typically do with the Gompertz-Makeham equation, right? You just show that once you're at ages where the exponential term is overwhelming the constant term, the Makeham term, then you get a straight line, and that's the blue line. You're all familiar with that. But the orange line behaves exactly the same way. And as you can see, the orange line is what I just did on the previous slide, where I'm taking the survival version of the Gompertz-Makeham equation, and I'm taking logs twice rather than once. and then there's this constant term that you have to add in. So they are identical once you're beyond about age 60. There's nothing between them. And that's what's going to be useful going forward. So as I've said, we're interested in these two particular assumptions, and we can actually accept those assumptions for any analysis of elderly humans. But there's another assumption that we have to make, or another feature of our data that has to be true, if we want to actually use this survival version of the Gompertz-Makeham equation for any kind of analysis. And this is it. We have to make sure that there are not many cases where people died at the same age. If people died at the same age, then we can't really, essentially our granularity goes away. We can't really have a Kaplan-Meier curve. We can't have a plot of the proportion of people alive at a particular age. But now we can go back to what I said about it being completely open what our granularity is for age. We can talk about how many years old somebody was when they died, but equally we can talk about how many months old somebody was when they died. And in particular, it turns out that for supercentenarian data, we can talk about how many days old they were when they died, because that's the data that the Los Angeles Gerontology Research Group record. We have supercentenarian data known to the day, and that turns out to be very handy. So, actually, I'm not going to go there yet. Hang on. Question then is, can we actually find anything out using this new analysis? Now, I started 10 or 15 minutes ago by mentioning how the standard analysis where we reduce each year of life to one data point, the probability of death, the mortality rate, that doesn't work very well for small data sets. But what I want to persuade you of now is that the reason it doesn't work is not inherent in the size of the data set. The reason it doesn't work is because that method of analysis automatically throws away a huge amount of statistical power. And this approach looking at survival, especially when these three conditions are true, retains that statistical power so that we can draw conclusions which are far more robust than we could if we did things the traditional way. So now I'm going to try to explain what I mean by that. And here's where I start to really realize that this is the first time I gave this talk, and I really don't quite know how to say this well, so I hope I'm going to be able to convey enough that at least you'll be able to ask the right questions later. Here is an example of the kind of analysis that I've just described. The y-axis here is a double log number of the sort that I mentioned earlier. The x-axis is age. And you may be a little bit shocked by the numbers there, but if you think about it, these are simply ages in days. 115 years is almost exactly 42,000 days. Just know that, all right? It's just for benchmarking. So what I've actually got here is the entire GRG dataset, the entire supercentenarian dataset from age 110 to 114. That's what we have here. And as you can see, the data points are very, very lined up. And we can draw a regression through it, and the R-squared is something like 0.9995. But here's the thing. That's nonsense. That's actually not an R-squared. And of course, the reason it's not an R-squared is because the data points are not independent. Any survival curve, any survival data set, is monotonic. Because once you're dead, you stay dead, right? So the proportion of people who are alive at age X is always less than the proportion of people who are alive at age X minus 1. So the data points are not independent, which means that this is not an R squared. You can think of it as a kind of nominal R squared, but it's not an R squared. So this is the question at the top. How can we get an actual R squared, an actual confidence level from the data that I'm talking about? Well, the answer is go to Monte Carlo. Go to Monte Carlo. You probably know how to do Monte Carlo analysis, most of you. You just make up data and see what happens and see how often it goes either side of what you're looking for. Now, what are we actually looking for here? Here's the first thing I want to emphasize. What we're looking for here is deviations from a Gompertz-Makeham curve. If you like, the null hypothesis, the default is that the probability of death of these supercentenarians will be rising exponentially, just as the probability of death seems to rise exponentially through most of the life course at younger ages. The question we want to ask is it actually rising exponentially, or is there some deviation from that? And if it is rising exactly exponentially, then we get a straight line on this plot, because of what I've told you earlier with that horrible algebra I showed you. But it might not be a straight line, so that's what we want to know. Now, it turns out that if you do this Monte Carlo analysis, you just throw random data at this kind of manipulation and you ask what happens, then yes, we're in. It turns out that this correlation, even though you totally can't believe the actual number, nevertheless, the number is actually even better than it would be with random data most of the time. This result means that, yes, we can, for practical purposes, view the supercentenarian data from age 110 to 114 as fitting a Gompertz curve. And there's stuff that I'm not even going to get into that's a bit horrible with regard to exactly what the coefficients of that Gompertz relationship are for this data. But let me just cut to the chase and tell you it's a bit flatter. The mortality rate doubling time is a bit longer than it is for people in the 70s and 80s and 90s, but only a bit larger. It might be up around 10 years rather than 7 years. It's definitely a very straight line. So, well, that's great, we've got this result, but it's very boring. So why am I bothering to come here and talk about it? The answer is, what happens if you go beyond 114? Now, it turns out that not very many people have lived beyond 114. Only 100 odd, in fact, in the GRG data set. But even with that tiny amount of data, 100 or 120 people, something like that, you can get some rather interesting conclusions. This is exactly the same analysis if you go all the way out to the very oldest people. That person at the top right there, that is obviously Jeanne Calment herself, who lived to 122 and a half. And you can see that it doesn't really fit quite so well. You've got this lovely fit out to 114, and then it kind of gets a little steeper. And then it gets a little shallower again. Now, it doesn't look very impressive when you look at it like that. But it turns out that if you actually do the numbers, it is impressive. The R squared that we get there, by Monte Carlo analysis, the same as I just mentioned, is very low indeed. What this says is that we can be more than 99% sure that the behavior of mortality for people at the age of 114 up does not follow the same exponential curve with the same Gompertz parameters as people from 114 down. It just doesn't. We can say that with more than 99% confidence. Now, what the hell? I have no idea. And I'm a biologist. I ought to have some ideas, at least, even if I don't know whether I'm right. But the fact is, it's a very paradoxical result. And in case you were beginning to worry that I might have got the maths wrong or anything, here's the result if we actually plot it a bit differently. What I have here is the same data that I showed you a moment ago with the earlier slope subtracted. I've just said, okay, let's go bang, let's go down. Let's just subtract that slope from this data, and then what does it look like? And it looks like that. And that's pretty damned unmistakable. That is not a straight line. That is not a horizontal line anymore, right? But the fact is, we need to understand it. Now, I do not understand it, but I sure as hell want to know. I sure as hell want to understand it, because it's real. This phenomenon of a kind of wall of death at age 115, 116 was observed by the gerontology research group several years ago. But, of course, they didn't know how to mathematically analyze it. They said, it looks like it's going up, really rather fast. What's going on? And all of the pompous academics said, oh, go away. There's obviously not enough data. This is obviously going to disappear once we have more data. Well, it turns out that the amateurs were right. The amateurs were right. This is real. So I'm going to quit the maths there. That's basically all I have to say about the analysis. And I'm just going to talk now at the end about how we might be able to move forward medically. In other words, I'm going to give a kind of one-slide summary of my day job. If you want to understand in depth the kind of stuff that I do and the kind of stuff that Sense Research Foundation does, well, there are about 1,000 videos of me online on YouTube, so that's probably the best way, though of course I'm happy to answer questions about any of that right now. And I'm grateful for the opportunity to give a very different talk today. But I will nevertheless spend a few minutes now just talking about what to do. Because, of course, the main reason why we study the oldest old is, in order, as I said at the beginning of the talk, in order to get some ideas about how we might keep all of us healthier into older ages. Because the people who get to these extreme ages, they didn't get there by staying alive for a long time in a bad state of health, in a senescent or senile state. Invariably, the way you get to be 110 is by getting to the age of 100 and the same state of health that your average person is when they're 80, and getting to the age of 90 in the same state of health that your average person is when they're 70. This is universal. So it's really something we need to understand. And if we want to understand how likely we are to actually do it, to develop medicines that do keep people alive for a lot longer in a good state of health, then, and how soon we're going to do it, then we have to ask how we're going to do it. We have to look at what's going on in laboratories like ours and where it's going, how much further there is to go before it hits the clinic, and so on. So I'm just going to briefly explain what we do. We can, and in order to start that, I'm going to just give you a definition of aging. And this is my three-word definition of aging. Metabolism causes damage, causes pathology. Metabolism, of course, is the word that biologists use to encompass everything that the body does to keep us alive from one day to the next. This huge, vast network of complicated processes. The thing is that metabolism creates damage. In exactly the same way that using a car creates damage to the car, rust and stuff like that gradually accumulates. Similarly, for any machine, whether it's alive or not, the operation of the machine creates damage. Throughout life, lifelong, that's really important. Damage starts to accumulate in our bodies even before we are born. And that damage is eventually problematic. It's not problematic at first, because the body is set up to tolerate a certain amount of damage without declining function. But eventually the damage becomes too abundant and we start to get sick. The pathologies of old age emerge in late life. And of course, eventually they become completely insupportable and we die. Now, this means that the main way that people have adopted to actually keep people healthy in old age was never going to work. That's what I call geriatrics here, geriatric medicine. Geriatric medicine is all about attacking the ill health of old age, Alzheimer's disease, most cancers, atherosclerosis and so on, attacking these things directly as if they were infections that could be eliminated from the body. It's obviously completely misguided because the damage that is causing these pathologies is continuing to accumulate as metabolism continues to operate. And therefore, we end up with any geriatric medicine, any medicine that attacks the consequences of damage, becoming progressively less effective as the person gets older. Just a completely misguided way of thinking. The approach that has been adopted over the past century by a small but determined community of biologists in response to the realization that geriatric medicine was never going to work has also not worked, unfortunately. It is essentially to clean up metabolism. The whole field of the biology of aging is focused ultimately on the idea that we might be able to actually reduce the rate at which metabolism creates damage. Call it cleaning up metabolism. If we could do that, of course, we would postpone the age at which the damage reaches a problematic level. But that hasn't worked either, because it turns out that metabolism is just too complicated. We just can't mess around with metabolism in such a way as to stop it from creating damage without having unintended consequences that stop it from doing the things we need it to do. So that's not worked either. But luckily, there is a third approach, which is the approach that I essentially pioneered and have been promoting for the past 17 years or so, which is the maintenance approach, the damage repair approach. Here what we say is, let's leave metabolism alone. Let's actually let metabolism create damage at the natural rates. If it can, then, if we're letting it do that, then we don't need to understand metabolism. We don't need to worry about the fact that metabolism is so impenetrably complicated. But still, we get the result. If we repair the damage periodically, then the damage will not get to the level that is problematic and pathogenic, even though it's still being created at the normal rate. So this is an approach that I believe is extremely promising, and it turns out that if you get down into the details of what the damage is that you need to repair, you can describe it quite simply. As you'll see in other videos that of talks that I've given, I normally describe damage as having just 7 constituents, 7 different types of damage that need to be fixed. And we're getting there. So if you actually want to know how long people born today are going to live, then think about some kind of trend line from the rate of increase in longevity that happened over the past century, because that is not going to give you anything near a reliable answer. The only way to predict how long people who are born today will live, or could live, is by looking in the laboratory at the kind of work that is being done and the kind of predictions that people like me are making about how soon that work will translate into medicines that actually succeed in this goal. That is how to predict longevity in the future. So I'll stop there. Thank you very much.